We continue with a discussion of other models that can be represented by differential equations, and that questions about the models whose answers can be found by looking at the solutions to those equations. Let's look at a model for, this time, the thickness of ice as it forms in a cold environment. When you look at water and how it freezes, the surface of the ice is going to freeze, surface of the water is going to turn first into ice. And of course that's because it's losing temperature to the air. Now what happens after that is you actually have a layer of ice on top of water that's still liquid, and then you have the air on top. The ice, though, that just formed starts to insulate the water underneath. And so it actually gets harder for the water to freeze that's underneath because it can't radiate heat as quickly. And as the ice gets thicker and thicker, there's actually more and more insulation, so it's harder and harder for the water to freeze over. This is why we don't get massive freezes all the way down into solid bodies of water like oceans and things like that. It can happen in puddles, but as we increase the thickness of the ice, it gets actually harder and harder for the water to freeze because it can't get rid of its heat to the environment as efficiently. Looking at the details now, if we let y of t be the thickness of the ice of time t, we're going to start measuring from the time at which the ice begins to form, which gives us a little initial condition. At time 0 there's no ice, but it's going to grow from there. That rate at which the ice forms, so rate, Q for derivatives, is proportional to the rate at which heat escapes from the water. Okay, so that's one rate already. So we've got dy dt, which is the rate at which ice forms, is proportional to the heat rate. And the rate at which the heat escapes is tied back to the ice thickness, because the more ice, the lower the heat. We're going to see this inversely proportional to the thickness of the ice. Well, that chain of proportionality is nice because we can actually use the same or one single constant to represent that whole chain. If we have dy dt is proportional to 1 over y, then the easiest way to write that down as an equation is proportional to means a constant times. And in this particular scenario, y is going to be increasing, so this should be positive, and y is going to be positive as well, so our constant here will be positive. We don't need any negative signs to make the relationship explicit. And this would be our differential equation. dy dt, the thickness of the ice, the rate it changes, is equal to a constant times 1 over the current thickness of the ice. Alright, now let's see what this predicts. How long will it take to form a certain level of ice? Things like that. Well, we've got dy dt is k 1 over y, and we take our usual approach. We're going to separate, and when we separate we'll have y dy is k dt, and our next step then is to integrate. Integrate, integrate. This is about as easy as it gets. That's kt. This is y squared over 2, and plus 1 constant. If we merge all the constants from both sides, we get a nice equation there. Or if we follow this up, we can solve for y, and actually we've got initial condition. Let's do that right now. Our initial condition was y of 0 equals 0. So let's use our initial condition, capitalized IC here, and everything's 0 at the initial condition, so we'd have 0 over 2 equals k times 0 plus a constant. Now, I think that pretty clearly gives us c equals 0. So we simply have y squared over 2 is kt, or y squared equals 2kt, or y equals the square root of 2kt. That is our function for the thickness of the ice. Thickness of the ice, that's y, over time. That's our mathematical prediction based on the thickness of the ice rate change being proportional or inversely proportional to y. All right. Once we have that, we can start making predictions about how long certain things will take, and let's take a look at how we can use information or data from particular data points or time points to do that. If we're told it takes 2 hours to form half a centimeter of ice, let's translate that. The time is 1/2. The matching y, let's get that right. The time is 2 hours, so let's say t is 2 measured in hours. The resulting ice thickness is 1/2 centimeter, so we can pick our own units here as long as we're consistent. Then how long will it take to form 2 centimeters? Pretty reasonable question. So we measure it after a couple of hours, it's 1/2 centimeter thick. How long will it take to get down to a full 2 centimeters thickness? Well, we use our solution. Our y is equal to the square root of 2 times some constant times time. This constant would have to do with the temperatures and the surface area, things like that. Well, we've got some blanks we can fill in. We've got t equals 2, gives us y equals 1/2. So we can sub that in. So we got 2k times t, which is 2. And so we get 1/2 equals square root of 4k. Square both sides, 1/4 equals 4k. K equals 1/16. All right. So that tells us that our actual solution for this environment is going to be y equals the square root of 2 times 1/16 times t, all under the root sign, or better known as square root of 1t over 8. That'll do nicely. Last but not least, we can answer the question, when is y equal to 2 centimeters? Well, we set our y value equal to 2, and we solve for the t value inside here. We can square both sides. 4 equals t over 8, and t is equal to 32 hours to reach 2 centimeters of thickness. All right. Now, one of the things that we can get from this is this equation is not sort of a nice one in some sense. It's not nice and linear. When we went from 1/2 centimeter to 2 centimeters, that's quadrupling the ice thickness. Notice it took only 2 hours for the first part, 2 hours here, but it's going to take 16 times that to actually get the thickness down to 2 centimeters. So we see the rates slowing down as t gets bigger and bigger, or as y gets bigger and bigger. And we can see that back in the differential equation. As y gets bigger, the rate of change of the thickness goes down, it gets smaller and smaller, so things start taking longer and longer to change. And that's what we see in our results here. The first 2 hours, things happen quickly, we get 1/2 centimeter formed, but it takes quite a lot longer to get down to the 2 centimeters, which is only 4 times as much, but it takes 16 times as long to achieve that. And we couldn't find that value out without going from our differential equation, which is the physics, to the solution down here, which is what lets us do predictions about time and when certain events will occur.